Hey, okay, so this is the first time that I've tried doing a video lecture, so we'll see how this goes. Um, we started talking about thermodynamics last week, and we started talking about the second law, and we defined a few things. We defined what a isothermal change is. That's when we have a process that's occurring where the temperature doesn't change. We talked about adiabatic processes where things happen, but our system is closed, at least as far as heat entering or leaving the system goes. It doesn't mean the temperature doesn't change. That just means that it doesn't leave the system and it doesn't enter the system going to or from somewhere else. So we've done that. We talked about macro states and micro states of a system, specifically with simple gas. And we talked about probabilities, and we took a statistical look at what the probability of something happening is. And basically, what it comes down to is that there are way more disorganized states than there are organized states for a closed system. So if we have that occurring, then the likelihood of things getting more disorganized over time is is very high. And the more particles that we have in our system, the higher that is. We drew some graphs and we saw how it basically, if you're looking at the disorganized states that are possible for a system, it basically made a spike right in the middle of our graph. And we could be really sure that that's where something was going to occur. That's where things were going to end up. So if we have a room that's got two gas molecules in it, odds are that the gas molecules are going to end up spreading about the room as opposed to all moving over to one side, which we never see that happen. It's more likely that they'll just spread out and fill the room, so that's what occurs. Um, so, one of the things that we need to talk about is getting quantitative with how we look at entropy. So, entropy is defined as, I'm going to write this over here. Entropy is defined as, okay, so the change in entropy. I'm trying to talk louder, so forgive me if you can't hear. Change in entropy is equal to the heat flow over some given temperature. And we could talk about a change in temperature, but if we want to talk about a change in temperature, then we got to start talking about calculus. So we're just going to assume that our temperature, that we're going to work with a fixed temperature. Um, so the second law says a lot of things based on how you interpret it, and sometimes those things, unless you've spent a lot of time working with the second law of thermodynamics, those things might sound like they're talking about entirely different things. It doesn't mean that one of them's right, one of them's wrong necessarily. Um, but with reference to entropy, what it says is the entropy of a closed system will never decrease. Okay, entropy won't decrease. Okay, so entropy is a measure of how disorganized or how random things are. And we're saying that won't decrease. So the randomness won't become less, which basically says that entropy is going to increase. Oh, well, okay. At best, it could stay the same. Things could be just as disorganized as they are and just hold, and that would be fine. We don't have any problem with that. But for a closed system, it's never going. The entropy is it's not going to become more orderly. That's just not going to happen um, unless somebody does work on the system. And we're going to talk about closed systems. So at best, it can stay constant. Um, in practice, for irreversible processes like friction, um, entropy is going to increase. Okay, um, and if we generalize that to include the entire universe, then we can say and we treat the universe as a closed system, then we can say that the entropy in the universe will never decrease, or it will not get more orderly. Okay? Why? Well, because there's just many more disorganized states for the universe to end up in, or a particular closed system that we're talking about to end up in. And so it's more likely that that's going to be what occurs. Things are going to get messier or more random, however you want to look at it. So let's talk about an example of an entropy increase in a simple system. So I'm going to draw some pictures, and you guys get to watch me draw a picture like you normally do. So let's start over here, and let's say here's my closed system, and I'm going to say that that system is insulated. Okay, and I'm going to start with a couple of reservoirs. And at this point, it doesn't really matter what our reservoirs are filled with. Um, we're just going to say that this one is hot and this one is cold. And we're going to call this T sub H. And we're going to call this T sub C. And since these are included in our system and we have something that's hot and something that's cold, those things are going to come to an equilibrium as far as temperature goes. So we're going to have heat moving between them. Notice that my arrow is pointing in the direction of the cold reservoir. Heat always goes from hot to cold. We've talked about that. And it's because if things are moving over here and they're not moving over here, it's more likely these things are going to move. That's just basically how that works. So we have a hot reservoir, a cold reservoir, and we know that those things are going to come to an equilibrium where everything's the same temperature. So let's see what that looks like. So I'm going to redraw my insulated system just to get a visual. And we've got our first reservoir, and we've got our second reservoir. And now we're neither hot nor cold, we're just warm. And the temperature, if they're both the same temperature, then this must be our final temperature. So they're both going to be T sub F. And notice that I do not have an arrow indicating heat, because once both of our reservoirs come to the same temperature, then we're not going to have a transfer like we did before. You could say that, at the very border between those two things, there might be a little bit of stuff going on, but the average temperature of the system is going to be the same. So what have we done now? If I want to do some calculations, then I need to pick a temperature to do those calculations at. And so if I draw like a thermometer over here, and we've got hot stuff at the top, and we've got cold stuff at the bottom. So T sub H up here, T sub C down here, somewhere in the middle. If we're assuming that both of these reservoirs are the same mass, then and the same material, we can put that in the middle and we call that our final temperature, T sub F. And I want to pick a couple of temperatures that represent what's going on. So I can pick a temperature that's here and call that T sub 1, and pick a temperature here and call that T sub 2. And we've essentially got T sub 1 is going to be not as hot as T sub H, but not as cold as T final. And down the same thing down here, T sub 2 is going to be not as cold as T sub C, but not as warm as T final. Okay, and I can just choose those temperatures to give me an idea of what's going on. And so for our change, our entropy change, the things that are hot are becoming less entropy. So we're losing heat here, right? Okay, so we're losing heat here, and we've got our temperature that we chose for things that are warm as T sub 1, and the temperature's increasing over here, so our heat flow is leaving this one, so we make our heat negative, and over here, our heat's going to be positive for T, and we're going to use our T sub 2. Now, notice there's nothing in the second law that says that entropy can't decrease. What it says is that the entropy for a closed system will not decrease. And this, if we just look at our hot water, our T sub H, it's within this entire system. So this part of our system, the entropy can decrease, which means that the entropy in this portion of our system is going to increase. And that's what we see down here. We see heat leaving, so our entropy here is decreasing. Over here, our entropy is increasing. And what will happen, well, let's say that. But just keep in mind that the second law doesn't say entropy can't decrease or that randomness can't become more orderly. It doesn't say that. It says for a closed system. Okay, so for this system, what we have, if we want to do some calculations, is we have our change in entropy is equal to our heat flow over T sub 2. I wrote 1, I should have written 2. Okay, minus our heat flow over T sub 1. Okay, so, and notice that these two values are the same. Okay, my negative sign that I drew over there for the heat leaving the hot reservoir is here now. So this value and this value are the same, but we're dividing those by these two values. And these values represent a temperature. Our temperature is cold down here, and it's hot up here. So our value, our quantity for our temperature at T1 is going to be a bigger number than T2. It's not going to be 25 degrees up here and 30 degrees down here. That's not the way our thermometer scale works. Okay, not if we're going from cold to hot. This number is always going to be bigger than that number. So we've got T sub 1 here, T sub 2 here, T sub 1 is a bigger number that's being divided into our heat, into Q, okay? So since we have a bigger number being divided into Q, then what's happening over here, because T sub 2 is a smaller temperature, then what that means is that this number is going to be smaller than that number. And if this number is always smaller than that number, then what that means is the change in entropy is going to be greater than 0. And if the change in entropy is going to be greater than 0, that means that the entropy is increasing for the system. So things are becoming more random, more disorganized, and less orderly. And consequently, this means that we're going to have less usable work, which we've talked about. So we need to talk about what you've heard people say, and there are a lot of dramatic people that like to point out, oh, the second law of thermodynamics has been violated, blah blah blah, and people will say things like the Earth was more disorganized in the beginning than it is now, before it was formed. The human beings are very organized systems, and we take random molecules and we turn them into organized systems. That's what happens when we eat or when we breathe. We're taking in molecules and other forms, and we're making them into more orderly forms that make us function and make us, so that we have a complex nervous system, a complex digestive system, and skeletal system, and musculature, and all that good stuff. I'm much more organized than the environment from which the elements that I'm made of comes. So we can also say that the whole planet Earth is a very organized system, but it's not a closed system. Just like you're not a closed system, you take in energy from other places. The planet Earth gets the vast majority of its energy from the sun, and will for much longer. The processes that are going on in the sun are causing the sun to be more entropic, and the entropy increase there is going to be much greater than the entropy decrease on the Earth due to the energy that we receive from the sun. So anytime you see a process that looks like entropy is decreasing, or looks like things are becoming more orderly on their own without any outside, it's not a closed system. It's just not. All right. So we need to summarize. And I'll move out of the way so that this equation behind my head can be seen. But I'm going to write some more stuff. So systems here's my cheat sheet. Systems tend naturally towards more disordered states. And entropy is a measure of that property. And entropy is a well-defined property of thermodynamic systems. And the second law says, you still see that? Yeah, okay. The second law says the entropy of a closed system will never decrease. Okay, so that's essentially the second part of our lectures over the second law of thermodynamics. There is going to be a third where we're going to talk a little bit more about consequences of what we've just discussed, and I will post another video for that. And I'm also going to do my best to come up with a lab for you guys to do at home, that you should be able to have the resources to do that. Um, but I'm going to hold off on that until I find out exactly what the plan is for our attendance. If you have questions, post the questions uh, in the thread that this video is attached to, and and I will do my best to answer them or give you examples if need be. Have a good spring, have a good extended spring break, and stay healthy.